tell everyone. You just need your moment. You just got it. You put it, got it. Got it. Yeah. Okay. So good noon to everyone. My name is William Liu. I'm the current chair of IEEE VTS New Zealand North chapter, and also I'm the current chair of the IEEE New Zealand North section side group. It is humanitarian special interest group on the humanitarian. And today actually is my great pleasure and to introduce Qiming Bao, a very excellent young researchers, and he will share his knowledge about natural language processing and also reasoning with us. So here I just have a short bio introduction about Qiming. Yeah, you can. Yeah, Qiming is very strong, so I have to shift a little bit of the video so you can see Qiming there. Okay. Yeah, and also, yeah, sorry, it's just, yeah, so you can see our face. Yeah, thanks, Qiming. Qiming Bao is a PhD candidate at the Strong AI Lab and the Liu AI Lab, the School of Computer Science, the University of Auckland, New Zealand. His supervisor are Professor Michael Whitbrock and also Dr. Jiamo Liu. And his research interests include natural language processing and reasoning. He had more than 2 years of research and development experiments, and he had published several top conferences in AI, NLP, reasoning fields, include AAAI and EAAI is ACL, and IGCLR. This is just short term for this top conference in artificial intelligence area, and other conference and journals. And also his research group is from the Strong AI Lab at the University of Auckland and also Liu AI Lab at the University of Auckland. So now it's my great pleasure pass time to Qiming. And so, okay, it's your time now. Okay, thank you. Yeah. Oh yeah, so you can share, oh, you already shared, right?
Yeah, can you see my screen?
Yeah, so probably, if you don't mind, maybe we just turn off the camera here so we can focus on the content. Okay, so probably we just start the video. Yes, great. Yep. So Qiming, is your time now. Yeah.
Okay, so yeah, welcome to everyone. So today I'm going to introduce the natural language processing and reasoning.
So is the voice clear? Just okay.
Is it clear?
Yeah, maybe you speak a little louder. Yeah.
Yeah. Okay. Yeah. Thank you for the invitation from William Liu. And yeah, so let's start. First, I will introduce our lab. So Strong AI Lab is led by Professor Michael Whitbrook at the intersection of machine learning, reasoning, and natural language understanding, with an additional focus on showing the best social and civilization impacts of increasingly powerful AI. And for Liu AI Lab, it's led by Dr. Jiamo Liu. So we are focused on the AI research group. And we engage in artificial intelligence research and development from both industry and academic sides. Our research interests cover a wide range of topics across the modern AI world, including deep learning, reinforcement learning, multi-agent system, natural language processing, and complex network analysis. And you can visit our official website here. And what we have achieved, Strong AI Lab has published more than 24 top-ranked conference and journals, including HCI, ACL, Triple AI, Qiming, NACO, AMAS, ICML, and so on. And we also win the Best Presentation Award for AGCAI. And Liu AI Lab has published more than 47 top-ranked conference and journals, including AMAS, CIGR, AI, NIPS, ICML, HCI, Triple AI, NACO, ICDM, and so on. And also some of them have high citations, like Mandy has more than 88 citations. And we have applied for several international and national grants and strong international and national research cooperation. So we welcome any student and postdoc to join our labs. So first of all, let's have a brief introduction for natural language processing. Basically, we can call it NLP. So natural language processing is an important direction in artificial intelligence. It studies various theories and methods, enabling effective communication using natural language between humans and computers. So natural language processing involves natural language, that is natural language we use in every day. So it's related to the study of linguistics, but it's different. So basically natural language processing is not a general study of natural language, but the study of computer systems, especially software system and algorithm. So we want to build up a good algorithm that can effectively communicate between human and computers. So there are many application scenarios, including machine translation, automatic summarization, text classification, question answering, and text semantic comparison, and so on. So I will introduce the development of NLP in this way. So first we will look at some rule-based approach, and then we look at static based approach, and then the current deep learning method, and then the which is the state-of-the-art transformer-based method. So first of all, let's look at the rule-based approach. So basically the earliest research work in natural language was machine translation. So in 1949, so Weaver first proposed the design of machine translation. But actually the method are limited by the computation resources, fixed rules, and linguistic and syntax grammar. But actually in real life, we know the natural language was very diverse. So it's their system can only handle limited problems. And then we have a static-based approach. Basically, the Frederick from IBM proposed a static-based method to avoid the design a complex rule and templates to process language in machine translation. So basically, we can, given the formula like this, so given the these previous words, W1, W2 to Wn, we can basically generate the probability of the sentence. So how to calculate the probability? We can given the probability of the first words, W1, and then based on the W1, we can calculate the probability of W2, and so on and so forth. So this is a very initial idea for this static approach. So in this way, we have one example, given sentence, 3 sentences. I'm happy today. I today am happy, and happy I'm today. So given these 3 sentences, so S1 is more likely to be chosen as the correct sentences because it has the highest probability compared with the other 2. That's basically the static-based approach. And then we have the Markov proposed an effective assumption that the probability of occurrence of any words I is only related to its preceding words, word I-1. So we can see the bigram static language model is based on this assumption. And we can also extend that to the n-gram model, so which costs more computation resources. So basically the bigram is, so we can see the formula is the next word. So word W2 is only related to W1, which is the preceding words of its word. And we have different gram. So we have unigram. So n is equal to 1, and bigram where n equal to 2, and trigram where n equal to 3. So given this sentence, if ugram is just independent words, and then we have bigram, so 2 words independent each other. And then trigram, we have 3 words as a unit to calculate the probability. So in real life, trigram probably the most frequent method to be used. So it's balanced the computation resources and the effective way to calculate the probability. And then we look at a very important terminology, which called the word embedding. So there's a question that how to transfer word into vector representation. So there's a word called one-hot encoding. So basically, this means one word has one encoding. So if given this example, word has this vector representation. And we have another word called words. Because it's different words, so it has different vector representation. But in this way, we can see if there's a new word, so we need to create a new vector representation. So in this way, the vector are too sparse and the vector are orthogonal. So we met a problem that the dimension of the vector can be too much. So there's a dimension explosion issue in this way. So how to cover this issue? There's a new method called word2vect. So basically we find there are some words are quite close in semantic space. For example, man and woman are quite similar words. And king and queen are also quite similar words. So can we have a vector embedding that close those similar words in vector representation? So then we come up this word2vect idea. So word2vect basically include two models. One is the continuous bag of word CBOW, which use context to predict the center word. And then we have the skipgram, basically use the center word to predict the context. So in this graph, we can show the word with similar meaning have closer distance. And then we look at the recurrent neural network, basically called RNN. So RNN is proposed to better address the problem of sequence learning and sequence translation. That is the problem of word-to-word sequence. So for example, given the sentence, high-speed trains drive at high speed on the rails. So if we swap the order of each word in this sentence, the meaning has been changed a lot. So the sequence in a sentence of the words is very important. So that's why RNN come out at this stage. But actually, RNN has an issue is when sentence length is very long. So RNN will suffer from gradient vanishing and gradient exploding. So to avoid those two issues, basically we have two methods. They call the LSTM and GRU. So basically they are the long short-term memory. It's called LSTM, and the gate recurrent unit called GRU. So basically, how they cover this issue is they add the gate mechanism. So for LSTM, they consider the three gate mechanism, including forget gate, input gate, and output gate. So in this way, they can filter out the unuseless information and keep the useful information, and avoiding the gradient vanishing and gradient exploding issue. And for GRU, it's actually modified the gate mechanism. So it's basically simplified the gate mechanism. So basically we can see there are too many gates in LSTM. So in GRU, we just have reset gate and update gate. So it's simplified the structure, but actually achieve the better performance. So that's why we have these two methods. And after that, we have a transformer. So transformer was proposed in Attention is All You Need, this paper, which is a multi-head self-attention architecture. So basically, transformer adopts global dependency, which breaks through the limitation that RNN-based model cannot be parallelized. So this is the main issue for the all RNN-based model. So basically, the transformer can parallelize training and better capture the long-distance text task. And we also find that there's so many pre-trained language model, including BERT, GB2, and GB3, are based on the transformer architecture. And they all perform the state-of-the-art performance on the machine translation, reading comprehension, and question answering, and other tasks. So the right-hand side is the main architecture for transformer. We can see this include two parts, so encoder and decoder. Left-hand side is the encoder. So all of them have the multi-head attention. So multi-head attention basically is a self-attention. So they had one head is one self-attention. So multi-head basically parallelize several self-attention and then concatenate the output and then to feed forward to the decoder part. So in decoder, they also have the multi-head attention. And so basically this is the main architecture for transformer. So normally they have 12 layers for each encoder and decoder. Yeah, and then let's look at the symbolic logic reasoning. So basically we can see the symbolic logic is a set of formal language that deal with how symbols express meaning and how reasoning can be carried out through symbolic means. So here's one example. So given these propositions, so including Bobby's big, all big people are rough, Bobby's rough. So conclusion is, so given the proposition A and proposition B, we can derive the proposition C. So basically, we can use the conjunction and using the symbol implication. So we conjoin the proposition A and proposition B. We can derive the proposition C as the conclusion. And then we look at an example for the symbolic logic program. So a normal logic program expressed by prologue can be seen as this way. So the first line, which is the rules, so it means, so Px, so given Qx, so if Qx is valid, then we have Px. So in this way, the capital X means the variable and the lowercase a means the instance. So given the QA is a fact, so we can use this rule. So if QA is valid, then we have PA is valid. So in this way, we can derive PA is true. So that's a basic logic program example. And we also have some other logic program example, including the, so in this way is the just given one fact. So we can match to ask this question. We have a question mark before the question. So is this proposition valid or not? So in this way, EL is correct. And then we ask another different proposition. So it's invalid. So it's false. And then we have the unification. So given the this proposition, so we have to match, because it's capital V. So capital V is a variable. So given the instance, so we have to make sure these two instances are the same. In this way, ODD has they have the same variable. So in this way, it matches the this rule. But actually, the belong instance is failed because B is not equal to D. And then we have the one-step reasoning. So given the, so one step means we use the rule once. So in this example, we have one rule and one fact. So we ask the question, is PA valid? And then we send the PA into the rule. So if PA, then we use the QA to ask into the rule. So if QA is valid, then PA is valid. So in this way, we can validate PA is correct in this way. But we cannot validate PB is correct because there's no supporting fact in the context. And then we can have the natural language reasoning. So we can understand natural language reasoning as representing symbolic logic in natural language. So we can basically first is logic of natural language, such as propositional logic and first order logic. And we also need to consider the diversity and flexibility of natural language, such as polysemy and a paraphrase of sentences, because natural language may have much more diversity compared to the purely logic program. And also reasoning, basically it means reasoning requires understanding existing information to obtain the unknown information. So then we have the three main category of reasoning. So deductive reasoning, inductive reasoning, and abductive reasoning. So they actually using the different condition to derive different conclusions. So for example, in deductive reasoning, given a premise and rules to derive the conclusion. And inductive reasoning is a given premise and conclusion to derive rules. And abductive reasoning given rules and conclusion to derive premise. And we can find more example in the later slides, and also you can check the more example from these two papers. So here's one example for natural language reasoning. So in this way, we have given input fact and input rules, and we have several questions. So we ask this question, whether it's true or false. So this is basically the task that we handle in our paper. So in this task, so facts represent as the proposition, and the rules, which including the first order logic. So for example, if someone is young and rough, then they are kind, and all rough people are green. So this is basically using the first order logic here. And firstly, we have the example how to we ask the first question. So the question is, as Bob is green, so is this true or false? But actually, given the facts we have, Bob is big and Bob is round. We have Bob, big people are rough, and all rough people are green. So we have these two rules. So given this fact, we can using two rules to derive the answer. So we can say Bob is green is true. So this basically we can see is a two-step reasoning. And then we look at the next question, Bob is kind, is it true or false? So given Bob is round, so if someone is young and round, then they are kind. But actually we can only find Bob is round. So we do not know Bob is young or not. So in this way, based on the closed word assumption, if there's no this fact exists in a given fact, we assume it's false. So in this way, Bob is young is false. So false conjoined are true. So basically the false. So we cannot use this rule to derive Bob is kind. So in this way, Bob is kind is false. And then we look at the next question is, so David is blue, is it true or false? So in this way, we look at, is there any David information? So if we want to say David is green, is blue, we need to know David is round and David is big. Actually, we can only know David is green and David is rough. So we cannot say we have no enough information to support David is blue is true. So in this way, David is blue is false.
Okay. So basically, you want the machine can think, they can jump, like they can really understanding something, right? Because basically it's not just one sentence, it's a several sentences. So they have to mapping out the rules, and they have to machine really understand the whole content or context.
Yeah.
Okay.
Hopefully they can learn how to use the rules and
yeah. This is much complex. Natural language processing is basically reasoning. Yeah. Very interesting. Yeah. Thank you.
Yeah. Thank you.
Yeah. Thank you. Okay, I got it. Okay. Very good example. Yeah.
Yeah, and so here's the research gap for our paper. So existing model, including deep logic and other Iron-based baseline model, have room for improvement in their reasoning ability over natural language. And we also find existing models are not good at out-of distribution or degeneralization, including 3 aspects. So one model be trained on shallow reasoning depth data set, and then test on deeper reasoning depth data set. And also one model be trained on the synthetic natural language data set and test on the data set with actual paraphrase natural language, so rewritten by human. And then one model be trained on unshuffled data set and test on shuffled data set. So basically we shuffle the order of fact and rules. So we find current model cannot really handle these 3 tasks.
So Paul, can you give us an example, like the first one, when model be trained on shallow reasoning depth set and test on the deeper reasoning depths?
Okay. So the reasoning depth means the rules, how many rules we use to derive a question. So in this case, to answer question 1, we need to use 2 rules.
Yeah.
So in this question, it belongs to the 2-step reasoning question. But actually, so for this question is the 1-step rule, because we just use 1 rule to derive the answer to validate its force. So in this point, if model being trained on the data set that's designed just use 1 rule to derive the answer, can those models be handled? This data set has
I see the
deeper
point. Like how many rules you need to train them? Yeah.
If we use a shallow reasoning depth, can this model be generalized to the task that require deeper depth reasoning depth, which means that which has a deeper rules that we needed. If model can do that, that means the model has really understand some reasoning.
Okay, it's like human. Yeah, that's challenging.
Otherwise, it's just do some pattern matching.
Yeah, that's will be really challenging because the machine can really understood that. Yeah, it's hard, I think. Yeah.
Yeah, this is one.
I see.
Out of distribution.
Okay.
Yeah, and we find the current model actually has this issue. So actually, current neural network cannot really handle this task well. And the second point is, if the model trained on the synthetic natural language dataset, which is the dataset that's generated by a computer program. So, but actually in real life, we know natural language has many diversity. So can this synthetic, can the model be trained on the synthetic dataset be tested well on the real world scenario? So this is also a—
So can you give us an example, like a simple example, so we can understand what you statement?
So all of these tasks are the synthetic dataset.
Mm-hmm.
So if we paraphrase one of the rules of fact, it actually changed the pattern of the language. So for example, so in this case, big, we can paraphrase big to maybe a heavy people. Rough, maybe heavy people are bad person. Actually mean the same thing, but actually it's using different words.
But now the machine actually, because now training by this word, so the machine actually have no idea.
They have no idea. They don't know what's the difference. Yeah, because those words are close.
What's a big, bad, and rough and bad? Okay.
They are the same similar words.
Okay, I see.
But they should be assume the same meaning.
If you change something out of the testing side, and the machine have no idea.
Yeah, machine have no idea.
Okay.
This
is the limitation.
Yeah, and the third one is the if we train the model on the shuffle data, unshuffled data, and test on the shuffle data. So this shuffle means, in this case, facts are grouped together and rules are grouped together. If we break the order, so if we shuffle the order of the sentences, so for example, the first sentence can be the rule, and then we have a fact. Because in machine learning model, probably we need to avoid the actually use some pattern matching, because they will find, okay, the first paragraph is a fact, second paragraph is rules. So we know, oh, I can find the all answer maybe from the rules. So I can guess some question without using fact. But actually we break the order. If we first have rules, and then we have fact, and then we have rules, and then we have fact. So we hope the model can learn the reasoning, not just related to the order of the fact and rules. So the order of the fact and rules is not important. The information is, so we're given this information, but we shuffle the order. We hope the model can still really learn the things, not just learn the order of the facts and rules. So that's why we do this task. And also we find the existing multi-step deductive reasoning data set like the pair rules and concept rules version 1 and version 2 have unbalanced distribution on the shallow and deep reasoning depths. So that means the deeper depths has a much less data set than the shallow depths. So that means, so it's quite weird because the deeper depths is harder, and then they need more reasoning rules. So they have, it's actually more difficult to handle the deeper depths, but actually they have less data set. But for the shallow depths question, it's actually easier than the deeper one. But actually they have much more data set. So that's why we find this unbalanced distribution issue. So we come up with the idea. So we build up a new data set called Parallel Plus. So it's actually focused on the reasoning depths between 2 and 5. So we increase the amount of data in this range. And then we add this data set into the training set. We hope the model can have better performance on the deeper depths task. Yeah, and here's basically our model overview. So the model is basically based on the deep logic model. And basically we have 2 modifications. So one is we use the word level embedding to represent the natural language instead of the symbolic logic program. And then we have the gate attention, which we bought this idea from the dynamic memory network class, which use deep gate attention and perform much better performance than the dynamic network without using gate attention. So first we have this word level embedding. So we use globe as the word vector representation. And basically the input representation there to the network is a sequence of 2 word level sentences for context and statement. And then the concatenation of context and statement will be fed into the gate recurrent union, which is GRU. And then we have the iteration. So iteration process is from deep logic. The iteration step consists of attending to rules and compute a new state using the each rule and updates the old state. So to apply a rule, we use another recurrent neural network called the inner GRU unified that process each rule of each rule. And basically the inner GRU unified need to learn unification between variable and constants. So that's basically the very important part. So that's the way that how each rule interact with the current state. So basic gate attention is first proposed in the dynamic memory network class. It achieves basically 100% test accuracy by using gate attention on baby deductive reasoning task. So in our task, we have the multi-step deductive reasoning task, but each step is a deductive reasoning task. And we basically give us the idea to integrate gate attention into deep logic. So basically, you can use gate attention to update the internal state. So here's the baseline model we use. We have basically 3 RN-based baseline models that we borrow from baby task leaderboard. And we also set deep logic as one of the baseline method. And then we have a transformer-based model, Roberta Large as a baseline model. So we use Glove as the vector representation for the all RN-based model. So we include a long shortened memory LSTM, the baseline method on baby dataset, and the dynamic memory network, which is one of the first paper use attention in memory network. And then we have a memory attention control network, so which is a classical method from memory network. So here's the dataset for concept group version 1 and concept group version 2. So the above one is the concept group version 1, and below one is concept group version 2. So it's actually different with parallel. So in concept group, they actually merge the fact and root together. So if you can see the parallel, we actually separate input fact and input root. But in concept group, we merge them together. So this data set is developed by Tim Hartil in Strong AI Lab. And for the concept group version 1, we didn't have the depth information. But in the concept group version 2, we add the depth information for each question. So we know this, for this question, how many depths do we need to derive this answer. And here's the data set description. So if you can see the first line is parallel rules. So if we basically, you can see that for the deeper depths, especially for the depths between 2 to 5, they have much less data set compared to the data set, compared to the depth 0 and depth 1. So this is why we come up with this idea parallel plus. So we focus on depths equal to 2 and depths equal to, between depths equal to 2 and depths equal to 5. We increase the number of training data set for this range.
Can I ask why the data sets in depth 0 and 1 are more than the deeper depths?
Oh, this is a good question. So because their data set is a synthetic data set, so generated by the computer program. So I guess the reason is they consider each example, and so depth 0 and depth 1 are the most frequent example they consider, but the depths, deeper depths, the scenario is quite less. So because in real life, depth 0 and depth 1 could be the more frequent scenario being used. So that's why probably the author from parallel, they focus on these two parts. Because the depth equal to 2 and equal to 5, the deeper depth is not commonly used in the real life. So I guess this is the main reason.
Yeah, thanks.
Yeah, thank you for your question. And also we find the concept version 2 and concept 2 version 2, full version and simplified version. They only focus on the depths equal to 0 and between depths equal to 0 and depths equal to 3. So they didn't consider the deeper depths more than 3. And so here's the more description of the data set. So we have different number of entity and relationship to build up the data set. And the shuffle rules means to reshuffle the rules in the data set. And then we have a depth tag. So for each question, we know whether the question is labeled with steps or not. And derivable means basically the question can be derived from the context. So all of them can derive the answer from the context. And then only F means negation as failure. So in this way, because we consider the question following the closed word assumption. So if the things is not exist in the fact, then we assume this thing is false. So we can use this as a condition to derive the whether the question can be derived to the answer or not. So here's a sample for negation as failure, only F. So you can see the yellow one. So if someone is not round, then they like the cat. Because we find there's no information about round. So if someone is not round, it's correct. So someone is round is false. So if someone is not round, it's correct. So then we can use this information to derive answer. If someone is not round, then they like the cat. So everyone should like the cat. This is the negation as failure.
So basically, you let the machine thinking like a human is, I think it's still very hard.
Yeah.
Because you have to using this, you have to make the rules, right? You have to pick up the rule, like to train them. I think the machine cannot actually tell which is the rules, which is the fact.
Yeah. So
right?
Yeah, they shouldn't. So if we tell the order, then they probably have remembered the order. Probably the first come out is the fact, and then after fact is rules. But if we shuffle the order, I think it's probably harder for them to detect which is fact, which is rule.
Yeah.
But we should make some challenges for them. So
Make
the computer smart.
Because if you mix the facts and the rules, how the machines actually know which is the rules, which is fact?
Yeah,
I think that will be really hard. Otherwise, or they have to analyze the grammar. I think this will be really hard. Even like human, when you read this, you take some time to link, to jump, to figure out, right? Yeah. So you let the machine do it. I think it will be really, really challenging. Okay, sorry. Very interesting. This is a very interesting thing. Yeah. I think it's really challenging for machines to do that.
Yeah. So in this task, we basically given this fact and rules and question. So the task is a binary classification task. So whether it's true or false. So in this case, we use Glove as word vector representation for the whole baseline. So we use this word embedding to for this whole baseline model, baseline model. And then in this case, we use parallel data set for the experiment. And then we compare our model, the IMA Glove GA. So basically the iterative memory attention with Glove embedding and the gate attention. And we also compare with other baseline. So the other RM baseline model and the transformer-based model. So in this case, we train all the model on the whole reasoning depths and test on the different depths test set. So D equal to 1 means depths equal to 1, and depths equal to 2, and depths equal to 3, and the depths small equal to 3, and the test set depths small equal to 3, and plus the extra natural language. So extra natural language means the extra paraphrase natural language rewritten by human. So in this test set, it's actually harder than the previous task because we add some real world natural language. And then we have depth small equal to 5 and depth small equal to 5 plus the actual natural language. So we find, so our model can perform better performance than the whole ARM-based model, but actually not that good at the transformer-based model. But we, because the transformer-based one is the pre-trained one, so our model is not a pre-trained one. So at least we beat all the ARM-based model without the pre-train. So then we have this experiment. So in this experiment, we compare our model and the deep logic model and the transformer-based model, Roberta large. So in this case, the simplify and full. So simplify means the data set has not been shuffled. So full version means the data set has been shuffled. So in this case, we want to validate the out of distribution generalization performance on the current model. So we find if the model being trained on the unshuffled data set and test on the unshuffled data set, so all of them can perform very well. But if we train on the unshuffled data set and test on the shuffled data set, the performance often decrease. But the Roberta one decreased a lot. So it's actually decreased a lot compared to the other two models. And then if we train on the shuffle one and test on the unshuffled one, so all of them can perform pretty well. And if we train on the shuffle one and test on the shuffle one, they also perform very well. So in this table, basically we find the existing model cannot really handle the case if we train on the unshuffled data set and test on the shuffled data set. So they actually fail on this case. So in this table, we actually do a more detailed experiment, which is if we train the model on the specific depths and test on the specific depth data set. So in this case, if we train the model on the depth equal to 1 and test on depth equal to 1 and depth equal to 2 and depth equal to 3. So we find the model can generalize very well. So that means the model is actually learning something about reasoning. And if we increase the depth, so that means we train the model only use depth equal to, and it's still perform very well. And then so mode 3 depth equal to 3 means if we only train the model using the depth equal to 3. And yeah, so often perform well, but not good at depth equal to 1 and depth equal to 3. So probably, so especially on the depth equal to 1 and depth equal to 2. So in this table, because the concept rule version 2 is not a very hard data set, so all of them can perform well, but actually, at least we can find the IMA-based model are better than the Roberta one, which shows that our model can perform better out of distribution performance on the, if we train on the shallow depths and test on the deeper reasoning depths, and then our model can perform better than the other baseline model. So here is the experiment we do. We want to look at, so we use Roberta large as a baseline, and we want to see how performance is on the deeper depths. So we can see the performance if we train the model using the depths equal, small equal to 2, and test it on the whole depths, whole reasoning depths. So we can see the model can perform well on the depths small equal to 2. But if the depth is greater or equal to 3, the performance dropped too much. So in this case, we find the model is not really understand and learn the reasoning in this case. But if we increase the depths, so we add the depths equal to 3, and then we into the training set, and then we test the model on the deeper depths. So performance increase too much, increase a lot. So that means in this case, the depths, reasoning depths, if we train a deeper reasoning depths, it's really help model to learn reasoning. So in this way, it's also validate our target is we trying to contribute a deeper depths. You can see but it still have some space to improve. And then we have this model. So in this model, we train the model on depth small equal to 3, and then add the extra natural language. So we find in this case, if we add the real world natural language in the training set, it can increase the performance as well. Especially on the test set, if we test it on another natural language, extra natural language scenario. And then we look at the depth small equal to 5. So in this case, we train the model using the reasoning depth small equal to 5. It actually can still perform better than the depth small equal to 3. So that means the reasoning depths can really help model to improve the performance. So here's the performance table that we add our parallel class into the training set. So PPT means parallel class. So we add parallel class into the training set. So we can see so basically all of the model can perform better than the previous model without adding our parallel class, because our parallel class focus on the data set. So the reading depths between 2 and 5. So that's why in this range, we can see model can perform can increase the performance on this range test task. Yeah, so that's basically the work from the result for my work. And then I will introduce some application scenarios that include, so first let's look at the search engine like Google, Bing, Baidu. So basically Google has announced that they use BERT, which is the pre-trained language model that I mentioned before. So they use BERT to improve the search quality. So for example, given the query, what can I do if I got COVID? So the Google will give you the treatment like this. So so basically they use the pre-trained language model to optimize their search quality.
So basically, the Google can understand what you really want, because this is a sentence. It's not like before we put keywords, they actually just follow the keywords. But now actually the Google really understand the whole sentence, like what I can do when I got COVID, right? So okay, so they're using this reasoning, and they actually looking for the expected result.
So yeah, it's more like the natural language understanding. So
It's like understanding the whole sentence.
Intention detection. So it will know what you really want, and then
Oh, that's interesting. I didn't really try this.
Give you the answer.
Yeah. So maybe next time I can ask where I have dinner. Like, and see if Google says.
Yeah.
Maybe I can try now and see what. No,
I think Google will give you some recommendation just around where you are.
Okay.
Probably.
So basically, Google understand the whole sentence now. Okay. Let's see what happens. What? Where?
Yeah, if you want to see more, you can look at the link here. So they give you some more detail about how the search, improve the search using the language understanding.
Okay, so basically, what I put is where I can have dinner tonight around the Epson, and then what actually pop up is the 10 best restaurant
in Epson. Okay. So basically, he got something about.
We just capture the keywords.
Yeah, but actually they have some logic. But what it means, like the first thing is like tonight, it probably not. Or if I ask, where have a special deal tonight? Where have a special?
So is your research focused more on the written language or the spoken language?
Written language.
So why not focus on the harder one, which is the spoken language?
So yeah, spoken probably is more related to speech language
Right.
processing. So
Okay.
Okay, interesting. I didn't really aware Google actually can do it.
yeah, they actually has give some introduction about how they use the BERT to improve the search, so you can have the link to.
But how about you take the word like I got? You just what I can do, COVID. See what happened? Because basically I got COVID, and Google can think, yeah, you got COVID, so it should be about treatment. So he's looking for the treatment. But if you take out the words like I got, what can do COVID? Yeah, I see what happened. No, I just thinking like how smart, what do COVID? I see what come out.
So
Oh, you see?
the government.
You see, what I put what do COVID actually is what is COVID and how is spread, right? So it's like because they didn't really find I got COVID, so this time they really just focus on the. But from human, I just say what do COVID. This is the keywords I put 3 keywords. But as human, I think we can understand like what I can do after COVID, right? But the result actually is, the first result of what is COVID-19 and how it's spread, and COVID-19 New Zealand. So basically, I didn't really provide enough word to formulate a logic actually Google can understand. So he still, in this case, very short word, so he just have to in COVID, what?
Like
Okay.
the pattern match. So you didn't give him the intention
Enough.
enough.
Yeah.
What do you want?
Yeah. So it's hard because as a human, actually, when we see the three, we actually quickly can figure out actually what I want, right? Because it's human. But for Google, he just look at the keywords. He really hard to really okay. But it's very interesting. But when you put all these sentences, you see the red thing come out. And this is really interesting. I didn't really aware of this. I'm sorry for the interrupt. You just keep going. I think this is very interesting. I got.
So what is the impact on what is the impact of the type of language, like English versus Mandarin, or what is the impact? Would it make the like if you design and train a particular model based on a particular language, that cannot be automatically ported to be used for processing similar information like in other languages? Is that?
So in my case, I just focus on the English as a.
But I think it will have very strong because I remember like if you look at Japanese, the grammar is totally different.
Yeah.
So if you're using the English algorithm to look at Japanese, I think he will lost. Or even you're using the English algorithm, you look at Chinese, because Chinese, the word can have many meanings. So sometimes maybe you have to, I think you have to using a dedicated algorithms on a dedicated language, because basically each language, their grammar and it's different.
Yeah. Even just focusing on English, you may have some oxymorons like pretty ugly, pretty and ugly together, or awfully good, awful and good. So it may cause confusion.
Yes, I think so. Yeah, you have to put this.
Yeah, that's a real world language.
Yeah.
It's not synthetic data.
So computer confused what actually you want to say. It's awful or actually good. But actually, you put awful good, and the other thing, it's damn good. Okay, like sometimes slang is damn good. Yeah, so it basically is good.
Or pretty ugly.
Yeah. Ugly, pretty. Okay.
So that's why natural language processing is hard.
Yeah, and also even the accent. I remember, sometimes even this is your lunch, and this is very kind of, and this is your lunch, and you feel, even the accent different. Actually, the people feel different. But how you actually interpret this sort of accent thing in the language is also very interesting, because yeah. Okay. Yeah, you can. No, it's very fun. I actually you talk about more about. I saw natural language is just about analyze the words. I didn't really. I mean, this reasoning part is very interesting. Actually. Because maybe that's what I think. Maybe because I just thinking like for VTS, I just thinking if it's a car, they look at a ball or a animal. Maybe they look same. So if you're using the vision, maybe it's a dog, or maybe it's something look like dog, but actually it's just a subject. So in that case, you can't stop or not. Because if it's not animal, I think you can actually get over. But if it's dog, you can't have to stop. So even you think about vision, they're using the vision to detect, but still they have to translate to the test, because the machine actually need to decide that I just keep going or I stop until they see. You have to put out this is dog. No, it's animal, I cannot. Or this is a ball. So ball is okay, I can get over it. I think actually, even people talk a lot about vision detection, but the vision have to translate to the test until the machine can understand the test, and then it can make a decision.
Maybe just one quick question as triggered by by William.
Yeah.
So given that this is a seminar organized by IEEE VTS, right?
Yeah. Just
so can you give some potential application of natural language processing for vehicular applications?
I think actually what I did is because in vehicle networks they talk about a lot of using of visual recognition, right? You see, it's a tree, it's a dog, it's a human, it's a ball. But if you really want to make a decision, the car like stop, you have to translate this to the text, to the word.
So you mean from vision to text?
Yes, I don't think actually it look at the vision and can take action. I don't think so, because it's a dog. So you have to think about it's really a dog. Dog is an animal. So animal is protected animal. So New Zealand, but it's a possum, right? The possum actually is also animal, but it's not protected in New Zealand. So you can get over if you decide it's a good possum is a dead possum. So if it's dog possum, you have to translate this to the dog. Always New Zealand protect, and then I have to stop. The automated car should stop. But if it's a possum, you have to look at the definition. Say, possum is okay. You can get over it. Kill it, no problem. New Zealand actually happy with that, so you can go over it. So image doesn't help. Until you really go to the test, and then you look at the test. What you can do on the test is it?
I'm not quite sure whether is it more efficient to directly process vision, or you convert from vision to text and then to the.
I think you have to put the test. Otherwise, it's dog or possum. So do you stop or not stop?
I think you need to understand the vision. So understanding of vision is actually related to some of the semantic information in natural language.
So you have to translate the image to the text, because in the text you can actually do the analysis.
I need to go and
Sure.
Yeah.
Okay.
Thank you. Thanks a lot.
Thank you.
So is it? I think this is quite interesting. If you think about the equal, right?
It's related to AI, I think maybe.
Yeah, but because you cannot actually using image to make a decision, right?
Yeah.
You have to understand what is image, and then depend on the rules or the laws. If it's all animal, you really need to stop, because one is dog, you should protect. One is possum, actually you can't kill. So you still have to understand what is really inside.
Yeah.
Okay, no, you can continue. I think it's very good point. Yeah, very good point. Yeah.
Okay, so the next application scenario can be the Google Translation and DeepL Translator. So actually, machine translation is the most successful application in natural language processing, and so often are using transformer as the core architecture at the moment. So they support text to text and speech to text and document to document across linguistic translation. And also more possible directions include low resources language translation, like Maori to other language and other language to Maori. So this can be the also quite interesting direction. And also the chatbot and personal mobile assistant, I think it can be related to the intersection between natural language processing and the VTS topic, because we can add some personal chatbot assistant in the vehicle. So in this case, like the personal mobile assistant and chatbot, like the Xiao from Microsoft and Siri and Google Assistant, IBM Watson are the application that consider natural language processing and question answering. So they can answer users' question and chat with user. So, and moreover, we know the medical chatbot like the Mandy is from Dual AI Lab, can be used to help patient improve the efficiency of medical treatment, and the patient can talk to the chatbot first, and then the chatbot will collect the required user information according to the predefined template, and then summarize it to the electronic record, so it can help doctors improve the medical treatment and simplify the process. And also we have another work, which is also is from my previous work, is actually combine deep learning and knowledge graph to build a retrieval-based medical chatbot platform called the HHH, and design an attention-based medical sentence similarity comparison algorithm, so which can effectively improve the calculation of medical text similarity. And also we have some COVID-19 with natural language processing. So this study focuses on predict COVID-19 patient shedding. So identify and protecting patients who are clinically extremely vulnerable from coronavirus. So basically this study focuses on the technology use multi-label classification for medical text. So they use the information published by United Kingdom, NHS, and the World Health Organization. So this paper presents a novel approach to predict the COVID-19 patient shedding as the multi-label classification problem. So this work is from the Strong AI Lab. Yeah, so that's basically pretty much for today's talk. Yeah, thank you for your attention.
Yep, thanks, thanks, Paul. And maybe you can open the, just open your video and we see if any questions. Yeah. Thanks for that. And okay. Yep. So thanks, Paul. And I just come here. So any questions? Any questions from the audience? Any questions? Like Julia, Paula, and Annika. Thanks for coming, Annika. Any questions from you guys? So also I just, or the people.
No, William, everything's okay. Yep.
Yeah, Paula, you can. I just show actually we have several in the local as well. And Bong Chung just got the meeting, so I have to go. Yep. Yes, Paula. Any questions?
No, William.
Okay. So how about Annika?
No questions on my end.
Okay, so maybe you can follow, but actually I have. I just thinking, the image, because I think about vehicle like a Bong Chung side, because basically, we are more interested on vehicle technologies. I just thinking because for vehicles there is a lot of usage using the vision to recognize, because when you have these autonomous cars, when they're moving on the road, they have to recognize all these things and they have to stop. They have to avoid, accident.
But now I'm thinking, actually the machine cannot understand the image directly. Is it? Because they have to translate the image to the text. Is it? Because like I said, okay, it's an animal, it's a dog, it's a person. So you have to translate the image, tell the machine what it is, and then you make decisions, right? So the image actually have to translate to the text, and machine can understand text. Because actually, even think about human, when we look at something, actually, the first thing we know, oh, this is a person. So it's okay, I can kill them. Or this is a dog, I have to stop. So it's still the image transfer the text. But probably for human, it's just very short, right?
Yeah, so because we want to make a final decision, for example, we met a dog, we need to stop or continue. So for this decision, we not only need to have some vision understanding, we also need to have some.
Because you need to follow the rules, because the rules you know like about who can kill, which can kill, which cannot kill. Right?
So because this is if this can be generally like a question which can kill or which cannot be killed, I think this is a vision to text.
Okay, and also I just look at look at this. Can you go back that long sentence? There is a lot of sentence there. I just thinking about how human figure out the rules and figure out your questions. Sometimes the rule is more like usually there is a advertive at the end, right? No, the previous one you have many rules, you mix with rule and facts. Yes, like this. The rules is something like usually you have 就是主谓宾怎么说呀？这是 you have a subject, you have verb, you have noun, right? Still you something like the last one you have the wrong. So you have to look at the grammar, is it? Because I just think if you mix the rules and the fact, how the machine actually pick up which is rules, which is fact. Do you need to look at the grammar or?
Because we just shuffle the order of the sentences. So for each sentence, it's actually generated by the computer program. So if we shuffle the order, it's not influence the grammar for each sentences. We just change the position for each and order for the sentence.
Okay.
But the sentence, we will not change the sentence itself. We just change the order.
Okay. Okay, so yeah, that's interesting. So any questions from you too? No? Okay. Yeah. Okay. So thanks, Bob. It's really appreciate you this nice talk. I think it's quite interesting. It's a lot of inspiring, but I think this is much challenging than I imagined. I think now I can see the natural language is very difficult. Yeah, and I think maybe something like the vision. I saw the vision is more complex, but now I understand. If you put these reasoning things in, I think natural language is quite challenging as well. It's very hard. Yeah. Okay. So thanks all, and thanks for your time. And probably we just finish here. Yeah.
Thank you.
Okay. Thanks, Paula. Thanks. Thanks all. Yeah. Oh, sorry. I just stop.